mentioned Gabe Grand, another student collaborator who is one of Jacob Andreas' students, and Tanja Stren, a student also co-advised by Josh and Vikash, as well as Noah Goodman, my advisor Vikash, and Jacob Andreas.
So our broader goal today in this talk is actually going to be to reflect based on many of the recent advances that we all know of modeling natural language, but I think also drawing on evidence from toolkits, other toolkits in AI, and evidence from cognitive science and from neuroscience on kind of the broader spectrum of different ways that we might think about building intelligent architectures that use and produce and learn from language, as well as more generally, I think what role language might play or could play in a computational system that we say thinks. And obviously this is a question that many people in this room, but many other people who probably aren't in this room have thought about, from philosophers of language to linguists and neuroscientists. And we thought it actually might be a useful exercise to kind of start by reflecting on the underlying answers to this question that are or aren't suggested by some of the most prominent directions that we're taking in AI research right now. And of course, right, one of the reasons why we're even asking this question at this scale, what is the role of language in intelligence, is in large part driven by this remarkable observation that we all know about from just a few years ago, which is, if you train these large and specifically transformer-based neural architectures as language models just to do this next word prediction task, with enough language data, they start to show behaviors that really suggest that there's something more than language at play. They look like they're thinking. They can induce patterns from just a few examples in data, or they can even read the definitions of totally novel words like Sachertorte in context and produce realistic sentences that appear as if they understand how to use those words immediately. And so a lot of the excitement, I think it's fair to say, around language models is that maybe for the first time, we're seeing something that is offering a scalable route towards implementing more generally intelligent architectures just by directly scaling, or largely by directly scaling the amount of language data that they're being trained to predict. And right, so what is the underlying idea here? What does this have to say about language? Well, I think it's fair to say that one of the dominant hypotheses that's underlying why we were even starting to see some of this behavior rests on kind of a two-part idea. One is something about the nature of language itself, right? It's the suggestion that language is sufficiently diverse and so broad, maybe because we suspect that humans express so much of their thoughts and such a diverse range of their thoughts in language, that being able to perfectly solve this task, to be a perfect language model, or at least a really good one, is essentially an AGI complete task. And maybe also one that conveniently, unlike other kinds of tasks like predicting all of the videos in the world, all the YouTube videos in the world, we have maybe efficient architectures to do and enough data to do. And I think it's worth noting that this doesn't actually really have to be a particularly strong hypothesis about what it is computationally that thinking looks like, or even how language necessarily is implicated internally inside the computational processes that we call thinking. Rather, it's really just a hypothesis about the nature of the language modeling task itself. And I think what a lot of people in this room would agree now is that, while that might be true about the language modeling task in principle, much of the most exciting research that we're seeing using LLMs right now actually isn't predicated on really the hope or the idea that just by scaling to more and more data, we're going to expect transformers trained and used in this way to actually solve that task or become perfect next word prediction models. And the intuition behind that, which I think many people have pointed out, comes both from the way in which transformers work, right? They're autoregressive language models that are doing a fixed finite amount of internal computation that only scales based on the previous linguistic context. And it doesn't really make sense that, of course, you can pose questions in language like arbitrarily difficult math problems or planning problems that intuitively require an amount of computation whose complexity doesn't actually depend linearly on the previous token context. And I think that's been matched empirically by lots of different observations about which kinds of sentences are hard to complete if you treat them as next word prediction tasks in this way, right? Hard arbitrary math problems or planning problems like these.
Right. So if you're thinking about the role of language, why are language models so big right now? As, oh, well, language just has all the evidence necessary to train to train something to think. Like Leo said, that's not actually committing to any hypothesis about sort of how language is used internally in thinking. The transformers computations are not necessarily doing anything linguistic as it's computing the distribution of the next word. But more recently, we've seen people use language models to solve these harder tasks by letting them think more. And what letting a transformer think more means is letting it generate more tokens. So in this view, thinking doesn't necessarily emerge just as predicting the next token. Rather, thinking happens in language, right? It happens by sort of producing a chain of thought or using a scratch pad or deciding that you're going to invoke a calculator or write some code and execute the code. The sort of hypothesis embodied, I think, by this line of work is that the role of language in an intelligence architecture is bigger. That language, or some kind of like running monologue of language, is the central controller of thought. And thinking is taking place primarily in language. What's maybe striking about these proposals is that if you ask most cognitive scientists or neuroscientists, they'd probably say this isn't the role that language plays in relation to general intelligence in humans, or at least it's not the dominant hypothesis. Until just a few years ago, this probably wouldn't have been the role that many AI researchers would have necessarily posited for language as the main controller or the main substrate of a running monologue that controls all thinking. And so we thought we'd review some of the background for what language seems to look like in humans as a basis for informing how we might build architectures that better capture those more human-like roles for language and thinking.
Yeah, and so I just want to be clear that we're going to do kind of a quick background on some of the neuroscientific and cognitive evidence about what language might look like in people. And our goal really isn't to push back in any way against these other kinds of paradigms for where language might fit in. It's rather to present, at a mode where we're really thinking a lot about scaling up language models as one really dominant role, what our other routes might be, because it doesn't seem like that really matches a different prominent intelligent architecture that's sitting here in the room today. So one source of evidence for the role that language appears to play in human cognition comes from neuroimaging data, fMRI data, suggesting how language is processed in the human brain. And at this point, convergent imaging data from many people, including Ev Fedorenko at MIT, Stan Dehane, and recent graduate students in our department, Kyle Mawald and Anya Ivanova, suggests that human brains have this language-specific network that handles many of the tasks that we associate with language. It's activated when people do tasks like listening to sentences, or reading them, or speaking, or writing words. And this is not just an English-specific network. The same general region is activated no matter what language someone is speaking. It even fires when they're producing constructed languages for people who come to learn and become fluent in languages like Dothraki or Klingon. And what is it that this language network does? Well, increasingly, one dominant hypothesis is that it actually does do something like next word prediction. And in fact, among many other kinds of alternative models, like people were earlier, for a long time, have been trying to do things like align word to vec to the brain. Transformer architectures really do seem to be among the best models that we have right now of the neural activity of this language network, specifically when they're trained on next word prediction tasks and not other linguistic tasks like NLI. But I think what we see in this neuroimaging evidence also highlights the ways in which the role of this human language network probably is not as the controller or the central seat of cognition. It's selective for language, and it isn't involved in many other kinds of thinking activities, even ones that might seem to involve symbols, like solving math problems or reasoning about logic and physics and social reasoning. Those invoke other reasoning regions of the brain, and language interfaces modularly with them. It can interface very generally with them, but it doesn't seem to be where the bulk of thinking is taking place. Oh, yes.
Oh, yeah. I just had a question about the next word prediction finding. So did you also try, say, like masked word prediction, and this is actually worse than next word?
Yeah, so I think they do compare, or like closed tasks are one of the alternates that they're looking for. And also, yeah, people should feel free to just shout out as we've been doing all along. So also, actually, you can see adult patients that suffer strokes that only damage this area of their brain. And we find that they can still think they can't comprehend spoken language, but they can still think about all these different kinds of tasks rented in different medium, like they can draw physical inferences from videos that they're watching. And conversely, maybe most tantalizingly, it's actually also possible to sustain localized damage that leaves you still able to produce these long, very relatively fluent and quite syntactically coherent sentences, almost as if they're maybe just like a very rudimentary and local word-based language model, while not really conditioning meaningfully on what someone else is saying. So they say, do you like it here in Kansas City? And this person says, yes, I am. Or really producing sentences that are obviously more globally meaningful or goal-directed towards the question. And I don't want us to over-index on those results, but they kind of fit in with this more coherent picture. And in many ways, I think this kind of recent evidence from neuroscience actually supports the broader picture of human cognition and the place of language in it that most cognitive scientists and many linguists have already believed based on what we see and have come to learn through developmental science, studying how kids think and where language seems to fit into that picture, right? And so a broad body of work at this point suggests that infants, well before they learn language of any kind or are speaking, already independently perform many of the tasks I think we associate with coherent thinking, from reasoning about physics to planning to drawing causal and probabilistic inferences. And language seems to be something that humans learn and scaffold on top of this structured basis for thinking. We take much less input data to learn to produce fluent language than a large language model. And humans that actually aren't exposed to any language input at all. So famously, there are these deaf children in Nicaragua who grow up in isolated hearing families, actually spontaneously come to produce early sign languages as a product of trying to communicate events that bear many of the hallmarks of the syntax that we associate of our own natural languages, like distinguishing between the subject who's punching and the person who's getting punched, suggesting that in many ways, the language we produce somehow externalizes the underlying structure of the thought that we already have. And of course, there are many other animals that we associate as being intelligent in some way, and that have been modeled using the models that we associate with probabilistic reasoning and planning that don't use language at all. So it doesn't feel like language is by any means necessary for what we think of as thought.
So, formalizing this picture of an intelligent system, one that's shared across animals and non-linguistic infants, and maybe captures some of the computations invoked in many of those thinking tasks that don't involve the language network in our brains, is both the central goal of a lot of cognitive science and has been a historic motivation for diverse fields within AI before the current sort of LLM-centric moment. So, if you open up Russell and Norvig's textbook, AI, A Modern Approach, you'll see an equation like this that's supposed to sort of capture what we believe about how intelligence works computationally, or a computational model of intelligence, where the idea is that an intelligent agent is one that has sort of structured internal world models that can be updated based on observations of the world and in which we can sort of predict the results of our actions, that the agent has some sort of values or desires that are captured in some kind of utility function, that the agent can do probabilistic reasoning over its observations and the possible actions it might take, and what their expected utilities are, and that it can do some kind of planning to optimize the value of its actions. Yeah.
Is it a normative statement or descriptive statement? Like, is it the case that we are defining intelligent agent to be having this kind of property, or it's like if we want to build intelligent architecture, we should have these?
Yeah, so I think it's a great question. I think some of the work definitely is coming at it from a normative perspective. This is like a definition of what rational action might look like, right? But I think there is a lot of work in computational cognitive science that sort of, in various domains, has collected a lot of evidence that people either recognize this as normative or behave like this in computation, according to the limits of what they can do computationally. In this architecture, the controller for thinking would be some kind of system that's capable of general world modeling and probabilistic reasoning, or planning and utility maximization, rather than sort of a primarily linguistic system necessarily. Now, largely, attempts in artificial intelligence to directly implement this equation by building out components that sort of map onto the different elements of this equation have struggled to match the computational efficiency and the generality of natural intelligence. But we have seen over the past couple decades or so the emergence of this new class of tools called probabilistic programming languages for building software that can solve probabilistic reasoning tasks, at least in limited domains. And these languages have been applied to create systems that do everything from perceiving cluttered 3D scenes more accurately sometimes than object detector neural nets, to interpreting and predicting economic trends more accurately than leading industry solutions like Facebook Neural Profit. And these probabilistic programming systems are enabling these applications with two key technical features. They feature modeling languages that let users express complicated probabilistic models of the world as programs, making it easy to write down rich probabilistic models that are defined in terms of expressive program-like components. So, for example, the probabilistic models behind these example applications are defined in terms of 3D renderers, symbolic planners, scientific simulators, and so on. And the second thing that probabilistic programming systems do is that they automate various mathematical operations on these models. And that automation makes it possible for users to concisely implement sophisticated algorithms for probabilistic reasoning, such as the variety of Monte Carlo and variational inference algorithms that power these example applications. So one way of thinking about these tools is as, kind of like PyTorch or TensorFlow, but instead of writing differentiable models and doing optimization, you're writing probabilistic models and doing various probabilistic reasoning tasks. So far, these AI engineering efforts haven't really made contact with language, with the sort of language model part of AI. Much like there hasn't yet been a concerted effort to take this classical picture of intelligence architecture and figure out how language might be richly integrated into it. So for the rest of the talk today, we're going to explore two different approaches for thinking about where language might fit into this picture and approach. So broadly, Leo's going to begin by talking about how an intelligent agent might incorporate lots of externally produced language, explanations, observations, questions, how an agent can incorporate all of those forms of language into the way that it updates its beliefs and decides how to act in the world. Then I'll talk a bit about systems that leverage language as a tool for thinking within its models of the world or its probabilistic reasoning algorithms. And each of these corresponds to very recent preprints of work. So I also want to give a disclaimer. We should really emphasize that both are preliminary proposals, and we're giving a very kind of speculative talk, not scaled architectural solutions yet.
Cool, right. So the first portion of this talk is summarizing work. If you want to read more, you can find this very long paper, From Word Models to World Models. That's up on arXiv, and this is primarily done with another student who's not here today, Gabe Grand. And as I just mentioned, the context for this work is thinking about how we can build systems that capture the breadth with which all the external language we hear seems to inform at least our human thinking. And what's clear, right, is that this role seems to be very broad. If we take the basic model of an agent with beliefs and goals, well, it seems like there's an incredibly diverse range of situations in which we can update our beliefs about a situation from observations that we express in language, or in which the goals of our thought are to answer questions that we specify linguistically. And these might implicate our knowledge of other agents, drawing on our intuitive psychology to reason about what they think and what they'll do. Or, we can talk about the physical world around us, what we perceive, and ask questions that require us to reason about what we see and draw on our physical intuitions. And of course, one of the remarkable things why we're also excited about language is that it doesn't just draw on what we already know. It's this means by which humans seem to learn and pass on profoundly new knowledge, whether that's new concepts that we define in words or learn from words, to really profound new theories and conceptual systems, right? Much of what we know about the world, the fact that there are wars, what wars are, legal systems, sciences, comes from information that it feels that we acquire from language in some way. But how do we do that? Well, I think one long-standing lens for thinking about language that's kind of persisted before the LLM-based moment is that what language is this external symbolic medium for communicating human thoughts. And the way that it does that is because there's some kind of general mapping function from our internal representations of thought into this external symbol system. That's language. And so in this kind of older framework, what it means to understand language or make meaning means mapping back from external sentences that we hear into structured internal representations. And what we explore in this paper is a general proposal that casts the meanings of language as these mappings or probabilistic distributions over expressions in a probabilistic programming language. And I'm going to come back after some concrete examples to how I think this relates to the conceptual role semantics that Steve articulated in the first talk, because I think there are actually some really deep connections here, the ways in which that might be one way to formalize or enrich some of those ideas. And this architecture, this proposal here also suggests how language can be integrated into a more general architecture, because it's one that already starts out with, as Alex mentioned, some kind of existing internal modeling language whose goal is to represent the world probabilistically, query those models, and specify what it means to draw coherent inferences over them. And it also suggests, I think, a framework for formally modeling the content of different kinds of sentences in language as the kinds of probabilistic programming expressions that they might map into. So And so in this paper, we begin by exploring how this proposal might be instantiated with respect to a bunch of different domains of reasoning, including general probabilistic reasoning, but also reasoning about relations or physics and social situations. And in all of these, we're going to propose that we might think about the language that communicates general conceptual knowledge about the world, definitions, or causal knowledge, as constructing these probabilistic expressions that are those that build up probabilistic generative models. And then in this framework, observations in the language, like there is at least one red mug in this scene, or Charlie is Dana's grandfather, construct formal conditioning statements, which update the state of this probabilistic model. And then questions map into query expressions that specify the formal target of probabilistic inference with respect to a model. And in this framework, where thinking essentially cast as probabilistic reasoning, we suggest that another way that we can think about the role of a language model, one that's much smaller, like the language network in the brain, is actually as a means of instantiating this meaning function in a way that we've really never had before, to protect these kinds of context-specific and previous discourse conditioned mappings from sentences in natural language into distributions over expressions that convey meaning in a probabilistic programming language. And so as a part of this long-running disclaimer, what I'm going to be showing is a really minimal implementation of this framework, but really intended as a pointer to different directions with which we might scale this approach to implement a more general interface between language and a range of different core cognitive domains. So just to be clear, concretely, in the examples that you see next, our meaning function is going to be implemented using Codex, right? An OpenAI model, much smaller than the state of the art right now, that's trained to learn joint distributions over language and code. And the probabilistic programming language we're going to show is Church, which is this very simple probabilistic programming language that supports kind of very general sample-based inference procedures. And our goal is to demonstrate how this framework might broadly interface between language and a bunch of different core cognitive domains. So first, to illustrate the basic sense in which a proposal like this might allow language to update an agent's beliefs and query a world model, I'm going to begin with a really simple toy example that actually draws on a bunch of prior cognitive science experiments in which real people were asked to draw various inferences about which teams of players might win different games of tug of war based on the games that you'd previously seen players win or lose. And so this is older work from Josh's group that demonstrated I think the sense in which this normative model, this Norvig model of probabilistic inference, actually in many ways predicts the actual behaviors and predictions made by humans using a very general probabilistic model of the mechanics of this tug of war game. And our goal here is to show how in our framework we can implement an interface between natural language and all of the core examples of this older experiment. So just to go through here, I think what you're seeing in this little toy example, the world model that's being defined on the screen is capturing the basic causal relationship by which properties of different human players might influence the outcomes of different tournaments that they play in tug of war. So for instance, here we're modeling players as having some internal inherent strength value, where strength varies approximately normally, but is this unobserved latent variable over different kinds of players. And we also think of players as having some kind of internal laziness value, which represents the percentage of the time that they actually don't act according to their underlying strength. How do these variables determine the outcomes that we observe of given games of tug of war? Well, the strength of a whole team of players depends on the cumulative sum of its player strengths. But if a player is deciding to be lazy in this game, they might not pull as hard as they could. And whichever team pulls with the most strength in a given match is going to win that match, yeah.
Did you design the primitives of strength and laziness, or Codex come up with the primitives themselves?
So in this one, we're looking at a model that's derived from the older work. So these are designed, but yes, that's later in this work, we're going to show some examples of how you can learn this kind of model from someone just talking about it in language, like the definition that I just gave. Right, and so again, this is a really simple example, but I think also one that actually captures a surprising amount of the basic causal knowledge that people have if you tell them that you're going to be listening to tug of war games, but sometimes people can be lazy and not pull as hard as they could. So how do we go about relating language in this domain? Right, well, one means by which we can induce a simple notion of a meaning function that actually fits the definition we just gave is by conditioning a language model both on this context-specific generative world model and on a few examples showing how language is mapped into sampled probabilistic programming expressions in this domain. And what we've done now, right, is effectively induce this kind of situation-specific contextual mapping from arbitrary new sentences to expressions that conditions both on the general prior distribution that codex is over language and code, and this kind of specific discourse thinking context of how language is being used in this situation. And there are clearly other ways to do this, some of which we'll talk about later, but we're using this example to illustrate just how much you might be able to do with this kind of minimal implementation, a notion of a model that translates between language to code. Right, so what kinds of language might we say here, and how might we think about them in relation to probabilistic pattern expressions? Well, a general proposition like Josh won against Leo gets translated into, or might map, we might think of mapping or meaning a condition statement. An observation that Josh won against Leo. If we make subsequent observations, like then Josh went on to claim victory against Alex, we can continue to kind of generally use this meaning function that we've induced to turn that into a probabilistic programming language that captures the fact that Josh won against Alex. If we then say that, even working together as a team, Leo and Alex still couldn't beat Josh in this game of tug of war. At this point, if we want to answer a query like, okay, wait, how strong is Josh? What we think of as thinking in this situation is actually sampling from the posterior over possible worlds from the generative model that we just defined, subject to the observations that we've just made. And indeed, that means that the meaning of a sentence like how strong is Josh is really a structured probabilistic inference query. What is the latent variable of that is Josh's strength? And what we see here is that given his track record, all these people that he's beating, even playing together, our inference is that Josh is likely a good bit stronger than average. And that also means coherently, we might expect that a priori, a new player we've never seen, like Gabe, is going to be unlikely to beat him. So if we ask, what are the odds of Gabe beating Josh, we see that we think it's somewhat unlikely. Oh, yes.
Yeah. So on the how strong is Josh, it seems like there's an interesting thing here where there's also an implicit question of what the word strong means in this context. And that, like, right, it's like not a number, it's kind of some like comparative adjective, and it's like probably a non-intersective. So I guess, is that something you think about in this framework, or should I just be kind of like ignoring this sort of issue?
Yeah, well, okay, so I think there's a number of ways that we can think about that. I mean, so one sense we could say is like, right, how strong is Josh isn't, the answer to how strong of Josh isn't a number, rather it's kind of this distribution over, this posterior distribution of various underlying strength values that we currently might infer that Josh has with respect to the generative model that we have. I think another kind of popular definition of various uncertain adjectives, like a word like strong, right, is that you have some internal threshold value, or the person speaking has some kind of internal threshold value that you must kind of jointly infer with respect to the context in what you've seen. And some of the examples that I'll actually give later, so right, there's kind of a long line of work in linguistics, including some work that treats that as like a pragmatic inference. I think some of the interesting work that we'll show a little bit later is that there are some ways in which you might think of this mapping function as actually being a general one that includes that notion of pragmatic inference, and also I think captures the sense in which, if you continually, are you really doing this kind of pragmatic inference all the time, or do you actually, in many general settings, like talking about the strengths of people, actually have some kind of cached older notion of strength that you can draw in? And I think actually this notion of large language models as just being this learned mapping function from language into expressions and code can also capture the sense in which that knowledge is amortized away. And you might not be having that inference. Yeah, Chris?
I guess I'm sort of just denying or ignoring what makes people so excited about large language models in their meaning representation and ability to do inference. I mean, because, okay, you've got sort of cooler probabilistic programming language on the right-hand side, but in some sense, the picture is still, this is semantic parsing like it was 2010 to 2015. And that, yes, you're using a large language model, but you're not actually using the excitement of a large language model as a representation system?
Yeah, and I think so. Probably each of us would have different answers to this, but part of what we're hoping to paint out over the course of this talk is, I think, some of the ways in which actually, right, of course, no one wants to say we're going to go back to kind of the brittleness of semantic parsing, but I think one thing that large language models actually give us, or one proposal in this talk, is that there are some aspects of the theory, kind of the classic notion of linguistics, and certainly classic notions of semantic parsing, that actually normatively capture a lot of what we really might want when we think about. So one answer for an AI system is, well, yes, in some way, we don't want to throw away everything that we're learning from large language models. And I think one answer to that is kind of the answer that I gave to Jacob, right? If we think about not always, in these examples, we're showing this very direct system in which, we always start with language and we always map into some sort of probabilistic programming expression. And that's where all of the thinking happens. And we might think, well, that doesn't totally make sense because there are lots of cases where, as you're saying, we have every reason to believe that large language models have learned a lot of latent information. They can do a lot of, they certainly have a lot of latent conceptual information, and maybe to some degree, they can even perform certain kinds of limited amortized inferences or reuse old inferences that they've learned from what other people have had. And so in the second part of this talk, we're going to show different ways in which, well, this probabilistic programming language itself doesn't necessarily need to be something that's isolated from what large language models have learned. It also can embed calls to large language models within it to kind of draw on that store of knowledge.
Haven't you gone back to the brittleness of semantic parsing? Because you're doing this translation into symbolic semantic representation, which you're either getting completely right or you're not, and it's brittle in the same way.
Well, right. And also, so no, I think I would say I don't totally think that the way in which we're using it, or the sense in which, or I think there are some ways in which this kind of broader definition in which you are saying, well, the meaning of the meaning of a sentence in language isn't just one probabilistic programming expression, right? That's what we're showing here for pedagogical purposes. But you might say, well, okay, right, how are you going to obey kind of the ambiguity of language? There are kinds of sentences that are definitionally ambiguous. So one example that we've looked at are sentences in which you say something like, Josh beat Alex and Leo, right? And you might ask, well, that's a kind of a classic syntactic construction. Does that mean that Josh beat Alex and Leo and they were playing on the same team, or Josh beat Alex and then Josh went on to beat Leo? And what we see, or generally what you might say is, well, the meaning of that sentence actually shouldn't be picking one expression or the other. It should be kind of the distribution over those possible parses. And that distribution also shouldn't just be something that we can determine in this totally context and sensitive way. It should actually depend on all of the previous patterns in the discourse. So if someone's continually been using this conjunctive and to refer to teams of players playing together, we should take that kind of discourse bias into account. And I think actually, right, this provides, or thinking of large language models as kind of generally having learned this broad joint distribution, but one that can be kind of conditioned quite richly both on, the content of this generative model. So, it's not trying to come up with a universal definition of strength. It's not even necessarily trying to come up with a universal definition of any of these words. It's thinking about how they might map contextually into the best possible expression in the context of a particular local model built for a particular situation. I think is, obviously related to, but attempting to address some of the brittleness challenges of semantic parsing in the past. I think another answer to this, right, is that part of the problem of semantic parsing previously has been actually that the mapping functions have historically been difficult to get right. Whether you were thinking about those as kind of old, hard-coded grammars, or many of the attempts to kind of learn these things via very domain-specific supervision. So you want to have a semantic parser for a particular robotics domain, you need 1,000 examples of sentences about that particular robotics domain, and 1,000 paired with 1,000 examples of programs that are operating on that particular domain. What we're seeing here is, I think, something that says no. What it means to learn language generally is to learn kind of this general mapping, right, between language and some kind of underlying representation. And also, right, one reason why we might want a system like this is because we want to be able to condition coherently on information that's not just coming from language. Right, we want to think about how a general substrate in which we might be told that Josh went against Leo, but we might also be watching videos that give us information about Josh's strength that convey our observations. We might also have seen pictures like the ones in the stimuli that we saw before, demonstrating the results of previous outcomes of matches. And I think, one thing that suggests is we want this kind of general substrate in which we can think about how those observations, including the observations from language, but without prioritizing language in any way, I think are coherently considered. So I think it depends on what part of semantic parsing you, I think the answer to that depends on what part of semantic parsing we think of as being the source of the brittleness that caused us to throw that paradigm into question.
Yeah, and maybe I'll just offer one more perspective. So one part of it is what Leo is saying. Traditional semantic parsing is brittle in two ways. One is, do you have broad coverage of language that you can parse into your system? And two is like how broad coverage are the set of query, like the set of semantic queries that you can actually answer. And I think what you're pointing out is this doesn't seem to address the second source of brittleness, which is that your system can only answer certain things, it can only reason about certain things.
I think the brittleness of the formal representation language that you're using.
Right.
Yeah.
That's
right.
true of large language model representations.
Right. So I think my sort of take on that is from a kind of AI engineering perspective is sort of a branching in two directions. One is, I think we have made some progress that, this is not really evoking, probably, toward systems that within restricted domains can reason coherently and probabilistically about a wide range of queries. So we have systems like this inference QL system that uses non-parametric Bayes to analyze huge data tables and come up with a model of that system that, or of your data that can answer all sorts of questions like, show me like which people in this data set are like probably overpaid given their experience or something like that. So in the same way that people are kind of excited about using natural language or using language models to parse into SQL, right? Because so much data is in SQL, and SQL is a very expressive language for asking questions about that data. When we have a probabilistic system, like a good probabilistic model of that data under the hood, it enables conversational patterns that are not enabled when you have like SQL as the database, because we expect our conversational partners to have coherent beliefs about the world, to update those beliefs in response to new evidence that we give it, to be able to report uncertainty and make sort of modal judgments. And so one engineering path is to take those kinds of systems and sort of build conversational interfaces to them that behave more like an intelligent person would behave and can draw inferences that you might not draw if you're just talking to a SQL backend. The other path that sort of we'll talk about in the next part of the talk is how can we use those representations that language models have learned to make the probabilistic inferences more interesting and more robust, less brittle, without sort of totally embracing the other kind of brittleness, which is the kind of brittleness that language models seem to have right now, which is that they don't really necessarily reason with coherent probabilistic beliefs.
So maybe, let's go into that next part.
Yes. Okay. Right. Well, so in the interest of time, I'm actually going to skip through some of the rest of this example, which I think is just more of what you've seen. But one sense in which I think, maybe a third part of the answer to Chris, I would say, is that, right, I think part of what this is trying to do is explore some of the ways in which we might answer without giving an answer in all the ways in which we might answer the ways in which language models themselves are brittle with respect to what we also want from a model of intelligence, right? We might suspect that when we ask questions like this, really what we are trying to do is specify some kind of normative query that captures formally a sense of, well, we want something like the posterior with respect to some kind of internal model of the world. And this is kind of the simplest means, or this is a very simple example of how we might formally impose that kind of structure, but one that I think can be elaborated on depending on the kinds of primitives and the ways in which you're thinking about what it is that the probabilistic program can express, right? So one way in which we might think about doing that is by thinking about probabilistic programs that themselves have access to other kinds of means of calling other different mechanisms in cognition, right? So I think I would draw a contrast here between the notion of the large language model as the controller, the one that's making the decisions about when to write little snippets of code and to execute them, when to call out to little planners and incorporate them, or stuff like the mind's eye work, right, where there's a language model, it decides when to call out to a physics simulator, but the way it interprets the outputs of that physics simulator is to paste those back into the language model context and try to draw inferences on them in turn. Rather, in this kind of framework, right, what you can kind of see the direction that this framework would be pointing towards is to say, well, on the other hand, we already have languages that allow us to do things like build expressive generative models over three-dimensional scenes that also capture things that we might want only from perception, like knowledge about how the shapes of objects tend to occlude each other, or incorporate rich models of physics, or that model theory of mind as taking place recursively in thinking about agents who themselves have beliefs about their own internal world models and are actually choosing their actions as planners, right? And in this kind of framework, you can point the way towards a kind of model that says, well, how is it that I might incorporate language into these kinds of models, sitting alongside these other kind of observations that I might make, right? So how might I think about the meaning of images that I want to generate that specify specific constraints, or imagination, or right? Yeah, go ahead, Jacob.
Yeah, I just had a clarification question. So you were talking earlier about having this meaning function, and then I think also we're mentioning something about like codex translating the question. So I'm just trying to understand which is that here, or is the meaning function going to come later? So that's maybe the first question. Then the other clarification is: so are these statements actually just being programmatically created from codex by prompting the text at the top?
Yes, that's right. So by meaning function in this framework, we say, well, there's kind of two general notions of a meaning function. There's a general joint prior, right, that codex is already, that it's learned between language and code. And then there's this kind of context-specific meaning function in the sense that it's conditioned on whatever's in the prompt, the generative model, and some examples of how language relates to expressions of this domain. So that's a meaning function. And yes, all these examples that you're seeing are one sample from that distribution. Right. And one of the things that I want to point to here, right, is I think it suggests a framework or another means of thinking about what it means for language to construct new concepts from definitions, or even come to construct new world models from thinking, like somebody in the beginning asked, right? So how, for instance, might we think about enriching an existing structured relational model with concepts that we learn from language? So for example, if we consider kind of a formal model of kinship relations, we might say that, well, the generative model of this domain is itself represented as a probabilistic program. It captures both the causal means by which people give rise to their children, and also the definitions, or one notion of the definitions of what it means to be something like a sister or a father with respect to this core notion of how family trees come to be. And so if you take this kind of general notion of the meaning of language as being the distribution over expressions that it creates in a probabilistic programming language, you might start to think how we can formally think about relating definitions for various kinds of relational terms, an uncle is the brother of one's parent or the husband of one's aunt. A sibling is a gender-neutral term for an aunt or uncle. That's the sibling of one's parent. Or this relational notion of a sister of one's father from a language that's actually not found anywhere on the internet. And I think the core thing that we want to suggest here, right, is why do we even have definitions at all? Well, one reason is one notion of what it even means to have learned the definition of this term is that it should drive coherently all of the downstream inferences that you make with that term, and it should graft onto the conceptual knowledge that you already have. And so you can think about forming new sentences directly that refer to someone's pa'ani or one's sibling in this situation, and expecting them to draw both on your existing conceptual knowledge of what it even means to have a family tree, as well as all the other conceptual terms for kinship that you may already have. And the same framework also suggests one mechanism by which we might formalize what it means to learn world models from language. So, as I mentioned, if we return to the situation that opened this talk, tug-of-war games, we might think about how the definition that I gave when I sat up here at the podium, right, saying there are people whose strength levels vary from person to person, people have a percentage of time in which they're lazy, strengths of the teams depend on the underlying strengths of the members of that team, and whether one team beats another just depends on which team pulls stronger that match. In this kind of setting is actually language, right, is building up the actual generative model itself. And you might think of a system like this that both learns these kinds of theories from language and then is appending to this kind of local problem-based context to answer arbitrary questions like the kinds that we gave, or condition on various observations like Josh being stronger than Leo with respect to this kind of local notion of what strength means in this particular problem context that we're thinking about. In the interest of time, why don't we just jump on to your section?
Yeah, thanks. So we've just been talking about how natural language can sort of be interpreted or semantically parsed to a probabilistic language of thought. But we haven't talked about how cognition itself, which is sort of, we've been talking about as the product of general purpose probabilistic inference machinery, might interact with language cognitively, or how our tools for our algorithms for inference, our model representations, might benefit from recent advances in language models. So in the rest of the talk, I'll sort of talk about this also very preliminary work that we just presented at a workshop at ICML that is more about a role for natural language and language models in this part of the picture. And one reason to think that natural language must play some role in this part of the picture is that, is that sometimes we set ourselves reasoning tasks whose specifications, what it would mean to solve the reasoning task correctly, must involve natural language. So for example, if you have an iPhone, you might have used the visual voicemail feature, which automatically but somewhat incompletely transcribes your voicemails. And these transcripts have gaps marked by underscore sequences of varying lengths, indicating Apple couldn't quite work out what was said. And an inference task that I sometimes face is squinting at these transcripts and trying to think, what could the person have said during those bits that it didn't transcribe correctly? And is it worth my time to listen to this voicemail, or am I pretty certain that I got all the relevant information from the part of the transcript that I've seen? So even if I'm representing that kind of inference problem in some kind of probabilistic language of thought and not in natural language, it must reference natural language, because a key part of the reasoning that I'm doing is about how long those gaps are, about what words could go in those gaps, how they fit semantically and syntactically with the words around them. And there are a lot of other tasks like this, where the specification of some reasoning problem must in some way involve language. Maybe we're writing something that has to obey certain structural constraints, like a poem or code. Maybe we're puzzling over a message from our advisor, trying to infer all the different meanings consistent with what they said. Maybe we're trying to figure out how to put together some words that we predict could achieve some desired effect in a listener. And beyond the fact that some inference problems implicate language in their specification, it seems like at least sometimes we sort of use language for thinking, right? Rubber duck debugging is when we successfully debug something that's been stumping us by just talking about it to ourselves or to a rubber duck. And I think this is the intuition also behind sort of chain of thought, Scratchpad, those kinds of innovations in language model land. But one reason why I'm drawing this distinction between task specification and algorithm is that this has long been a really important distinction in probabilistic modeling and inference. And it's something that I think we lose when we move just to asking a language model a question and hoping that it gives us the right answer. So, you know, in the kind of work that our lab does in modeling and inference, we sort of separately create a model probabilistic program that encodes a task specification as a posterior distribution we want to sample from, and separately an inference program that compositionally encodes some kind of algorithm or strategy for solving that inference task. And when you use a probabilistic programming language to do this, you get some benefits from taking this approach of separating model and inference. We know that we have soundness theorems guaranteeing that as computation increases, the inference is going to approach the posterior. We have automated tools and tests for measuring how accurate our inferences are relative to the model with finite computation. And we also have gradient estimators that help us tune any parameters of our inference programs to be better inference algorithms. And beyond being useful properties for engineering, these guarantees also reflect some key aspects of human cognition. We can often think more to reach more accurate conclusions. We can critically evaluate the extent to which our current hypotheses actually make sense given our model of the world. And if we repeatedly face the same kind of inference task, we can train ourselves to get better at solving it. So something we've begun to explore is whether adding LLMs to this picture might let us both specify various linguistic tasks as formal probabilistic models and enhance our inference algorithms by letting them do some of their thinking using language as a tool. So I'll first talk about the modeling side of things. So we all know that an autoregressive language model defines a probability distribution over sequences of tokens. But we rarely just want to sample that unconditional distribution. You know, in the same way that in order to use a SAT solver, we need to reduce the problem we care about to a SAT formula, to use a language model, we need a reduction from the task instance that we care about to a prompt. And the idea is that we're saying that the conditional distribution of the language model, condition of that prompt, is somehow a good specification of the task that we want to solve, or a good approximation of the task that we want to solve. But unlike the reductions to SAT, of course, this reduction is lossy. One problem is that sort of hard constraints, sort of instructions that we give the language model might be, you know, it might fail to follow them. So this conditional distribution, P task, is not really the specification that we have in mind. It's just some close thing that we can get. Another problem is that the entropy of this distribution may not meaningfully reflect uncertainty. So you may have seen in the GPT-4 paper that on multiple language tasks, multiple choice tasks, where there's some multiple choice question and then the language model is asked to output A, B, C, or D. Before they did any RLHF and instruction tuning, if they create a calibration plot where they plot sort of, you know, of all the answers in which GPT was, you know, 0.4% confident, how often was that the correct answer, right? GPT-4 is strikingly well calibrated. And that's what you might expect from a model that's doing a very good job of next token prediction, of matching the distribution of language. When it's uncertain, the loss function is telling it it should allocate its mass, its probability mass, according to that distribution. Whereas after RLHF, the calibration is shot. And this is also what you might expect. Even if the humans who were sort of providing the human feedback in RLHF preferred the right answer, okay? The distribution that you get after performing RLHF with the objective that's commonly used for RLHF sort of creates a reduction in temperature. It's equivalent to reducing the temperature of the parts where the human feedback is exactly aligned with sort of the correct answer. And so it becomes overconfident. And, you know, this is very prompt dependent. I don't mean to say that this is like always going to happen if you go and use GPT, but I went and used GPT 3.5 to do this like infilling task, and it did it correctly, but also every time that I generated at temperature 1, it gave me basically the same answer. So if I want to think of this distribution as sort of representing uncertainties, that I can make decisions about whether to listen to my voicemail because it might contain things I don't know, this P task is not up to that task. So our idea is to, instead of reducing to a prompt, reduce to a probabilistic program that may call a language model, which is sort of a more flexible way of specifying what P task distribution we want to sample from. And I know I'm running low on time, but the idea is that these models can mix calls to the language model with conditioning statements and other logic. So in this probabilistic program for this infilling task, it is in a loop going through each sort of blank that we need to infill, sampling a random number of tokens that should fill that spot, sampling those tokens, and then observing the next sort of fixed fragment, or conditioning on the next part being a fixed fragment. And this just lets us specify a model that doesn't just have a prefix prompt, but sort of has a prompt with blanks in it. I haven't said yet how we're going to sample this, but the idea is that this defines a specification for the task that we want. And similarly, we have programs that sort of specify a variety of tasks that involve sort of thinking with language, right? We can condition on hard constraints if we want to parse into a formal grammar or write a haiku. We can do kind of a product of experts model using multiple prompts. So maybe I want to think about a fun fact that's about both London and Paris. Well, you could just ask the prompt, hey, please give me a fun fact about both London and Paris. But you could also create a product of experts model where it has to come up with a completion that is both a completion to the sentence, a fun fact about London is, and a completion to the sentence, a fun fact about Paris is. And that's kind of a hybrid where the idea of and both is symbolically encoded, but we're still using the language model's representation of knowledge about fun facts and these cities. Similarly, we can sort of represent reward steering or classifier guidance by conditioning, by sort of soft conditioning on a reward function. And we can also include things like, hey, please generate a gloss of this code that when I try to semantic parse it back into code, gives me the same code I started with, things like that. So those are model programs for specifying various tasks. We need inference algorithms for actually sampling from these distributions. And so far, we've been focusing on sequential Monte Carlo inference algorithms. And we kind of have a default version of this method and then fancier versions of this method that are necessary for harder tasks. In many ways, sequential Monte Carlo looks like beam search. You kind of keep multiple hypotheses around, you extend them, you reweight them in a model-specific way, and then you resample, which is kind of like the part of beam search where you sort of downsample from your big expanded beam back to your beam size. But unlike beam search, sequential Monte Carlo, as you scale up the number of hypotheses that you're using, instead of converging to an argmax of your objective function, converges to the posterior distribution, sampling from the posterior distribution. And this sort of default version of SMC has worked for a few simple tasks that we've tried it on. For example, if I want a completion that follows my favorite physicist is probably and my favorite writer is probably equally well, SMC can give me Richard Feynman. I really admire how he communicates complex ideas so clearly. Or if I want to finish the Fed says, but only using words less than 5 letters, I get the Fed says it will taper, but rate hikes are still years away, or something like that. And it's worth noting that if you do something like token masking to enforce this constraint, you just forbid the language model from generating anything that's longer than 5 letters, you get all sorts of weird completions. It's different from the posterior here. You get completions that, set up an idiom that it could only complete if it used a word longer than 5 letters or something like that, right? And then it just gets very confused and writes ... read more or something. It tries to come up with some context in which the sentence would be cut off early. And for infilling tasks, we get a variety of samples that sort of fit semantically and syntactically with the text, but infilling tasks can be made much harder than this one. So I don't want to claim that this method yet solves all these infilling tasks. So for harder tasks, we think we're going to need to use fancier sequential Monte Carlo algorithms. And both of these sort of steps can actually be extended in various ways. We can use better proposal distributions and sort of better reweighting strategies that are trying to guess, okay, are we on the path to getting a good sample here? And we think that techniques that have already been developed in the literature for proposing good things in line with constraints or sort of discriminating whether we're likely to land in a constraint could be good ingredients to put here. But the important thing is, and this is the very end, the important thing is all of those things become part of the inference program. And there are still guarantees that as we scale up the number of particles, we're still targeting the original specification of the model. So all of those heuristics or biases we don't just trust them blindly. We don't hand the keys to those techniques. We still have a specification that we can understand. Okay, I'll stop there. Thanks.
Great.
we're a little bit behind time, so unless there is a burning question, no burning questions. Let's break for tea and maybe Zahar Torta, and you guys can talk to the speakers. And at 11:30, we are going to